Solve. So in number A, we have, for the first equation, x squared minus 3xy plus 2y squared equals 0. And for the second equation, we have x squared plus xy equals 6. So the first thing I think of when I think of a system of equations, especially nonlinear equations, I think of substitution. So when I see the bottom here, I see this xy, and if I move the x squared over, I would have 6 minus x squared. And then if I took this and I plugged it in the top equation, one thing I'll realize is I still have an x and a y in the equation, which is something I'm trying to get away from, and that's why I use substitution. The reason for the substitution is because I'm trying to get it an equation in terms of one variable, and that doesn't work that way here. So then I notice this 0 here, which then tells me, oh, maybe I can factor this here. So then that's what I take a look at. And it actually does factor. That's going to be x minus 2y and x minus y equals 0. And since I have a product here of this times this here that equals 0, then either x minus 2y equals 0 or x minus y equals 0. So now we can solve these two equations, and all I'm going to do is move the negative 2y over, so I really get x equals 2y. Because in essence, I'm just trying to take this top equation and solve it, or get an equation in terms of x equaling some function of y, or vice versa. And then for the next equation, I get x equals y. So now I'm just going to go through, and since now I have this equation here, from the first equation, I'm going to plug it in the second equation. Wherever I see x, I'm going to plug in 2y. So that's going to be 2y squared plus 2y times y equals 6. So you can see that I just plugged it in the second equation here. And 2y squared is going to be 4y squared plus 2y squared equals 6. And the 4 and the 2 I can add because they're like terms. So that's going to be 6y squared equals 6 divided by 6. Y squared equals 1. And now I'm going to square root both sides. And that's going to be y equals plus or minus 1. So now to get the ordered pairs, because remember in solving a system we're looking for points, I'm going to take this positive and negative 1 we have for y now and plug it into this equation here. And when I plug in a positive 1 in for y, 2 times 1 is 2. So I get the ordered pair, 2, positive 1. And then I do it again for the negative 1. So when I take that negative 1 and put it in for y, that's going to be 2 times negative 1, which is negative 2. So that's going to be negative 2, negative 1. So these here are my ordered pairs for this problem. So then I can get rid of all this here. I don't need it anymore. And I can just move this over here. And then we can get started on the x equals y. So then for the x equals y, now I'm going to plug that into the second one. Wherever I see x, I'm going to plug in y. So I'm going to get y squared plus y times y equals 6. So that's going to be y squared plus y squared equals 6, which means 2y squared equals 6, which means I divide by 2. Y squared equals 3, and y equals plus or minus the square root of 3. So now I'm going to use this equation because that's the equation I was using for this one. So then that tells me then my x is going to be the same as my y. So the positive square root of 3, comma, the y is going to be a positive square root of 3. And negative square root of 3, the y is going to be negative square root of 3. So there's our answers. So now we have all 4 of our answers for this problem. There turned out to be 4 answers. It's quite a bit. So now that's our answer for our first one altogether. Let's move on to B now. Now I'm looking at these log equations here. This one's quite different. So what I'm going to do is I'm going to get all my logs on the same side because I'm thinking about simplifying logs and then using my equivalence property. So before I move it over, though, I'm going to use my power rule. Take that to the inside of the log. So I get log base 3 of x equals 2 plus log base 3 of y squared. And then now I'm going to move it to the other side, so I'm going to subtract it over. So this is going to be log base 3 of x minus log base 3 of y squared, and that's going to equal 2. So now I'm going to put my logs together because I can by quotient rule. It's going to be log base 3, and it's going to be x over y squared, and that equals 2. Now I'm going to use my equivalence property, so 3 to the power of 2 equaling x over y squared. And I'm going to solve for x just because it's easy. So x is going to equal 9 minus y squared. Now I'm going to do the same thing with the bottom equation. So first I'm going to put the power to the inside. So that's going to be ln of x equals ln of y to the 5th. Now we can handle this a little differently here. I can take both sides and plug them into my e to the x. So this is going to be e to the ln of x and e to the ln of 5. And then from here, what we can do here is those cross out, and I get x equals y to the 5th. So there's my other equation. So now we have this system. Oops. So those are my two equations now. And I'm going to find out where those are equal. And then from there, I can determine if it's a valid value, because remember, I can't take the log of a negative number. Okay, so anyways, so now let's take this and plug it in the first equation. So that's going to be y to the 5th equals 9 to the y squared. And then I can move that 9 over. So y to the 5th minus 9y squared equals 0. And then I'm going to factor here. So I'm going to factor a y squared out. So I'm going to end up with a y cubed minus 9 equals 0. So for my two equations here, I get y squared equals 0 for the first one, and that's this one equaling this. And that's going to result in y equaling 0. So that's my first result. Now the other result is y cubed minus 9 equals 0. So then when I solve for it, I move the 9 over. That's going to be y cubed equals 9. Then I'm going to cube root both sides. And I don't have to worry about the plus minus when I cube root, because the index is odd. If that index was even, then I would have that plus minus scenario. So this is going to be y equals just cube root of 9. So that's going to be my y value for that one. Now, for my equation there, I can pick any one I choose to plug it in for. And I'm going to take this and plug it in the bottom equation wherever I see y. So that's going to result in x being, now I'm just going to write this here in terms of its rational exponent. So I'll slide that over, and that's going to equal 9 to the 1/3 power. So I'm just going to put that in place of y here. So that's going to be 9 to the 1/3 power squared. So then that equals, oh, no, not squared, but to the 5th power, excuse me. Yeah, it's because that's here. Okay, so then that's going to be 9 to the 5/3, and that's going to be my x value. So I get one value with the second equation, and one value with the first, which is there. So the two ordered pairs we get are going to be 0, 0, and the other one's going to be 9 to the 5/3, comma, 9 to the 1/3. But we do have a problem here, because now we have to take those points and go back to the original equations, because we pulled them from the logs. And remember here, if I have an x or a y that's a 0, I can't take the log of a 0. So this 0.00 is not going to work for us here. So we do have to keep that in mind, the domain that we're dealing with for both functions or both equations as well. It's very important here, so that we don't get something that's undefined. The second one works fine. Those are just positive numbers or greater than 0. So that's going to work for every log here, for either x or y. So this here is my only answer where they intersect. 9 to the 5/3 power, 9 to the 1/3 power. Just remember, that's a big deal there once you get an answer, to make sure it makes sense. So for the first A, we had 4 answers, and for B, we had only 1 answer. And again, we had to get it down to where we could work with those functions algebraically, so we did the exponential rules, or I should say the exponential form of the log equations. So there's our answers, and they call that an equivalence.